Hi guys. So today we are going to be looking at the percentage composition when the formula mass is given to you. So this is again a parts to whole problem, and in this case let's just focus on solving these problems using the significant figures rules. That's the significant figures rules, and that relate to the addition and subtraction and multiplication and division. So when you add and subtract, your final answer should have the lowest decimal point. And when you multiply and divide, the lowest significant figures is going to be in the final answer, okay? So now we are going to look at one example of ammonia, very simple example of ammonia, okay? So here you are given ammonia NH3. Okay, so first let's calculate the molar mass of ammonia, and we are going to determine here that what is the percentage of nitrogen and what is the percentage of hydrogen in this 1 mole of ammonia, in other words, or in that certain grams of ammonia. Okay, so first of all, the molar mass of ammonia. Excuse me, 1 mole of ammonia contains 1 nitrogen atom and or 1 mole of nitrogen and 3 moles of hydrogen. The weight of nitrogen is 14.01, and the weight of the hydrogens is 1.008. 1.008. And so this comes out to be 14.01, and this is 3 times, this whole thing comes out to be 3.024. 3.024. Now you're going to add. So here you're going to see that this is 2 decimal points and this is 3 decimal points. Okay, so when there are 2 decimal points and 3 decimal points, your final answer should have 2 decimal points. Okay, so now we are going to take this, let's calculate this whole thing, comes out to be 17.03. 17.03, and you leave the 4, drop off the 4 because 4 is less than 5. So 17.03, this is basically, you know, in general for the molar mass we call it 17.03 grams per mole, but it's also another unit is 17.03 atomic mass units. So in this case, since we are just doing the percentages, we are going to just follow the atomic mass units. Okay, so let's do this now. So the percentage of nitrogen is equal to 14.01 atomic mass units of nitrogen divided by the total formula mass of ammonia, which is 17.03 atomic mass units of NH3. All right, times 100%. Okay, 100%, and this comes out to be 82.27% of nitrogen. So that's the percentage of nitrogen in that the formula mass. Then comes the percentage of hydrogen. So we have 3.024 atomic mass units of hydrogen present in 17.03 atomic mass units of NH3 times 100%. And this comes out to be a total of 17.76%. 17.76% of hydrogen. So if you were to add the 82.27 plus 17.76, you are going to get 13, 10, sorry, 10, 10, 10. So that roughly, you know, so that's the total. Okay, so that's how you can also check your answers if you get it right. So that's the amount. Okay, now let's look at one of the learning check problems that relate to a more complex molecule, which is, let's say, learning check here. Okay, so the learning check problem is C9H8O4. Once again, this is an aspirin molecule, and this is C9H8O4. And in this molecule, what is the percentage composition? Calculate the percentage composition of carbon, percentage composition of hydrogen, and percentage composition of oxygen. So in this case, you are going to first calculate what is the carbon percentage, hydrogen percentage, and so you are just given this particular molecule. That's it. So what you're going to do is, in this molecule, you are going to calculate the molar mass of C9H18. Sorry, this is the H18. My mistake here. I'm sorry. This is H18, not 8. Okay, C9. C9H18O4. There's a little bit of this mistake here. Let me just find this out, one thing. Okay, so sorry about that. So it was C9H8O4. So that's actually, this is aspirin. Okay, so in aspirin, C9H8O4, so first is we need to find out what is the percentage of carbon, hydrogen, and oxygen in that. So that's all we're given. We're given the formula. So first thing you're going to find is the molar mass of C9H8O4. So how do we do that? So you are going to take 9 atoms of carbon. Each is weighing 12 grams. 8 atoms of hydrogen, each weighing 1 gram. 4 atoms of oxygen, each weighing 16 grams. And here you are going to get the total weight. When you add this whole thing up, you are going to get 180.159. So this whole thing, when added together, this is 180.159 grams per mole, or another way of writing is 180.159 atomic mass units. That's fine. Okay, because we are just doing the percentages here. So the total mass comes out to be this when you add it. So I'm going to just put it here. Add. Okay, now we will get the percentage of carbon. Percentage of carbon is going to be, so we see that, oh, wait a minute, sorry about that. Okay, so we see the percentage of carbon. There are 9 moles of carbon are present. Each of those 9 moles of carbon is 12 grams, and this whole thing is present in 180 grams of C9H. So actually it's 180.159, sorry about that, 180.159, 159 grams, 180.159 grams of C9H8O4 times 100, okay, times 100. And this thing, you get this, when you do the math, this will be 9 times 12 divided by 180.159, and that comes out to be 60%. This whole thing comes out to be, so carbon percentage is 60%, percentage of carbon. Next comes the percentage of hydrogen. So we see that there are 8 moles of hydrogen, and these 8 moles of hydrogen, each is weighing 1.008 grams. That is the molar mass of hydrogen. divided by the total, the molar mass of this 180.159 grams of C9H8O4. That's the molar mass of C9H8O4 times 100. And you're going to get the percentage of hydrogen, which comes out to be 4.476%. Okay, so here, if we are looking at, like we talked about, we are going to be looking at the significant rules here. So we are going to see that in this case, you see that this is you're dividing. So this is just one significant figure, two significant figures for the 12, one significant figures for 9. And then we have 1, 2, 3, 4, 5, 6 significant figures here. Sorry about that. 6 significant figures here. 6 sig figs. I'm going to just write here. So that's just 1, and this is 2 sig figs. This is 2 sig figs. And what should be your final answer? So we can't have 6, obviously. 1, so it's just 60%. It makes sense. So just leave it that way. Okay, and moreover, for the whenever you have these exact numbers, you have they're not factored in, because exact numbers will have like variable significant figures. So here again you have 1, 2, 3, 4 significant figures, and there are 6 significant figures. So that is why we brought in 4 significant figures in the answer. Okay, so some of it, you have to also use your common sense, when you do these, does it make sense or not? So anyway, so this is one thing. And then comes the other one, which is oxygen. Okay, so the percentage of oxygen is that in this molecule we have 4 moles of oxygen. Okay, so 4 moles of oxygen, each is 16 grams, and that whole thing is present in 180.159 grams of C9H8O4 times 100. And you're going to get here, one more time, let's look at the significant figures. 1 significant figure, 2 significant figures, 1, 2, 3, 4, 5, 6 significant figures. So your answer should have, let us see what you get here when you do this more further. Multiply, this becomes 64, 4 times 6 divided by 180.159. So this is 64.00 comes out to be, and divided by 180.159, okay, times 100. So when you do this whole thing, it comes out to be 35.52%. Okay, so here we have the significant figures. When we do the math, when we calculated the 16 times 4, the lowest significant figures, 64, right? 2 significant figures, basically. 64 is the 2 significant figures. And then this, so, but we need to put 0.00, so we get this thing. So this is the 4 significant figures here, a lower significant figures multiplying. Okay, so that's the thing with these, each of these components. So if you were to add 35.52 times or add 4.476, and you add the other one, which is the other one, 60.00, so 699.9 and 9. So approximately, comes out to be 100%. That's just approximate. Okay, so that is determining the percentage composition. Okay, and we can look at one more example here, which is the example of iron, Fe2O3. So Fe2O3, what is the mass percentage of iron? So let's do it in the next example. Okay, that's a little bit, it gets too big videos, so I need to make them small. Okay, so anyway, so I'm going to see you in the next video in which we'll do it for Fe2O3. Okay, this is important because, why is it important? Because very soon we will be doing the empirical formulas, determining the empirical formulas and the molecular formulas. So that is where all these mole calculations and all these, these come to play. Okay, so thank you so much, and thanks for watching.